This video will talk about how to track moving vehicles using RF techniques or radio frequencies and Kalman filter. Specifically, it focuses on three different ways of applying the Kalman filter. So we plan to do three videos. One is using the linear Kalman filter with uniform and non-uniform data error distribution, which is this one. And then we will produce another one to show the extended Kalman filter. Extended Kalman filter are used for nonlinear systems. And the third one, we'll recording about the time difference of arrival and angle of arrival position estimation using the Kalman filter. In vehicle tracking, identification and tracking of vehicles for air, ground, or sea are important for safety, security, and protecting of the assets and other reasons. Um, Different IF measurement techniques, including radar, has been known to be used. For unmanned vehicles, they radiate IF signals, and their controller also radiate IF signals. So those can be captured or monitored and help determining the ID and the tracking of vehicles. So the subject that we use for demo here is unmanned aerial vehicle. And different methods and antenna designs or different capturing method and antenna designs, including phase arrays, has been used to capture the UAV IF signals and analyzing them for ID and tracking purposes. The captured data, however, contains a lot of errors due to noise, propagation loss, and so forth. And Kalman filter can be used to significantly reduce the errors and accurately determine the UAV's position over time. Kalman filter is the de facto standard for use in positioning and navigation. Common applications include guidance, navigation, and control of vehicles, especially for aircraft, spacecrafts, and ships. Other uses include cognitive radio, applying machine learning into IF radio, for example, or sensors, and Kalman filter used to filtering things out, make the sensor become more accurate, or robotic motion planning and estimation, and even in economic theories and things, you can use it for modeling. The Kalman filter is a statistical method or algorithms. It uses measurements that fed into it over time and to make accurate estimations. So in a way, it is a machine learning because it have to learn over time. Mathematically, the set of metric equations are used for it to predict and updating of the information or the output. If the equations are nonlinear, then the model become a nonlinear model, and then we would have to use the extended Kalman filter. The computation used to calculate these equations and values and variables and things can be very intensive because the data, there are much data and multiple error conditions or variables can be applied to equations. The demo that we're about to show has three parts, and we used a flavor of MATLAB called Octave to develop the models and to run feed the data into and to display the results so that you can see. So the first part of the demo is to track a UAV, go from the US West Coast to the north of the United States and then to Florida. And we use the XY coordinates tracking method or latitude, longitude with uniform noise. The second part, it used a different kind of data, use the distance and angle measurements from the tracker to the object, and also it apply uniform noise error. The third part, we will introduce a more realistic model of error by doing non-uniform error. And also we use the distance and angle measurements. So the next part here, our people will demonstrate a demo.
In this video, we will see the simulation of flight path tracking system using Kalman filter. In the setup, we assume that a central tracking system receives measurement of flight positions in real time from different regions of a monitored area, and its objective is to plot the flight path on the image of the map that we can see on the screen. Now, there is a noise present in the measurements which causes the errors due to several environmental and system noise effects. So, the Kalman filter, which is integrated in the tracking system, aims to remove that noise and give us the best possible estimate of the true flight position in real time. Now I will briefly explain the setup used for the simulation. We are currently in the Octave simulation environment. Now I will take a quick look at the code or program which is used for this simulation. In this program, first we manually need to generate the data used for flight trajectory. So in the problem definition section, we can specify the different coordinates over which the flight will go. We assume that the altitude and the speed of the flight is constant, and we specify it in the program. It will only change the direction at the specified coordinates. We use the sampling time of 1 second, and we capture or generate about 18,000 to 20,000 of data points for the flight path, which is equivalent to approximately 5 hours of data in real time. After generating the data, we introduce the noise into the measurements by using the error percentages or error deviations given in the program. These noisy measurements are then fed to the Kalman filter so that we can get the estimate of the true flight path. Now I have switched to the command window in Octave, and now I will run our first simulation. For this simulation, we assume that the measurements received by the system are X and Y coordinates themselves. And as you can see on the screen, we are printing the configuration used by the tracking system and Kalman filter. So in the system state, we have X coordinate, Y coordinates, which are longitudes and latitude. Then we also include velocity along x-axis and velocity along y-axis into the state. The system state matrix of a Kalman filter represents the state update equation used by the system. In the process covariance matrix, we specify the amount of error that might be present in the calculation, such as rounding errors. Now we have generated the data required for this simulation. Now we will take a look at the. So as you can see on the map, the true flight path can be seen on the red line. So after generating the data, so we are generating x and y coordinates to feed into the system. Now we have specified the error percentages as 3.7 and 18.5. These error percentages will contribute to the noise and generate the noisy measurements first. So what we are seeing now is the noisy measurements being plotted onto the screen. As you can see, it is very hard to determine or estimate the flight path from noisy measurements due to significant error. The dotted line shows the true path. Now we will take a look at how the Kalman filter estimation looks like. So in the dark blue line represents the estimation by the Kalman filter. As you can see, it tries to converge on the true flight path despite the large noise present in the measurements. So now we have completed the simulation. The results regarding the errors can be seen in this graph on the right side. The yellow represents the measurement error. They are about of magnitude of 4 to 5 coordinates, and similar with the y position errors. And the magenta color line represents the final estimation error after applying the Kalman filter. As you can see, compared to measurement error, the estimation error is very low. We can also see the result after measuring all the data that was present. The root mean square error is used as a standard to determine the residual error present in the after the system has run. So initially the measurement errors were 2.16 and 4.11. However, after the Kalman filter estimation, we get the errors of 0.17 and 0.24. So we are able to significantly reduce the amount of error and filter out the noise using this Kalman filter. Now we will take a look at another design of Kalman filter, which will use different sets of measurement. Now in this system, we will be using typical radar measurements, which is a Euclidean distance from an object or a flight, and the direction of the flight with respect to a reference axis. And we will use the rate of change of distance and rate of change of direction in the system state as shown here to predict and estimate the actual flight position. The measurements include only distance and the angle of the flight, and we add noise as before. Now we have already seen how the true flight path looks like, so we will skip ahead to the actual simulation of the noisy measurements. So we can see the noisy measurements being plotted over the map as before. And now we will see the estimate of the Kalman filter from these noisy measurements. Now the difference between these two designs is the type of measurements. So instead of directly feeding x and y coordinates to the system, we are actually feeding the rho and phi, which is a straight line distance and then angle. So as before, you can see the results in the right hand side figure. You can see that the measurement errors are significantly reduced after estimation, and we get final root mean square errors of 0.21 and 0.36. Now, if you notice one thing in the graph, that the the noisy measurements, which are in sky blue color, are actually distributed uniformly around the true path of the flight, which is not the realistic case. So we will try to use the non-uniform distribution of error to see the working of Kalman filter in that case. Now I will use the same design of the Kalman filter, that is using the distance and angle measurements. This time the noise introduced will be non-uniform. So I will skip to the simulation because all the system configurations are going to be same as before. Now you can see the system is plotting the noisy data, and you can clearly see that it is non-linear. The effect of noise is much more significant in this case, since it is non-uniformly distributed across an XY plane. But you can see that the Kalman filter in the dark blue color is still able to estimate the actual flight path with pretty much same accuracy. You can see the measurement errors are actually distributed non-uniformly, and however, you can still see that estimation error is significantly reduced using the Kalman filter. Now all these results are stored in a log file so that we can compare different designs. They are stored in the project directory. So I will quickly go to that. As you can see, we recently ran 3 of these designs. The first one used x and y coordinates as measurements, and you can see the root mean square errors in both x and y coordinate measurements and estimations. We used total of 18,061 measurements for each simulation. In the second part, we used rho and phi, or the straight line distance and an angle of a flight, as measurement. And in the third version, we used the normal distribution or a non-uniform distribution of error to see the results. So using this system, we have demonstrated the ability of Kalman filter to filter out the noise and give us the best possible estimate of the actual measurements in the real-time flight path tracking system. Thank you.